Welcome to today's A4 tutorial. Today I'm going to talk about a problem that's been floating around the internet, and it comes under various names. The most common phrase that I've heard referred to it as is the 1869 MIT entrance exam. And the problem's presented as being unsolvable by some people, and of course it isn't. First of all, let me explain. The problem, it's very verbosely worded, using a lot of quite archaic language that we don't see used much anymore. But the basic problem comes down to this. We've got a right angled triangle like this, and the triangle has been bisected, and each of these are at 90 degrees. And this length is a length of 9, and this is a length of 16. And the question basically says, solve for unknown lengths. And some people look at this and they say, yeah, I understand that this is 25 long, but we don't know any of these other lengths, so the question becomes, how long are these? And the path to solving this sort of problem is almost a Pavlovian response. Whenever you see a triangle, you should be thinking a squared plus c squared, b squared equals c squared. Now, with this bit of knowledge, we can solve this, and it's quite a straightforward thing to do. First of all, I'm going to label some things in here that aren't labelled yet, and I'm going to call the length of this x, a standard unknown variable. This one I'm going to call y, and this one I'm going to call z. So if we apply this theorem to this, we can see quite easily that 9 squared plus y squared equals x squared. Okay? And similarly, if we apply it to this triangle here, we can see that 16 squared plus y squared equals z squared. Right angle triangles, applying your basic theorem. And if we look at the one overall, we can see that x squared plus z squared equals 9 plus 16 all squared, which is 25 squared. Now, it should be fairly obvious that we've already got a term for x squared defined in terms of y, and we've got a term for z squared defined in terms of y. So all we need to do is substitute in these terms, and that gives us 9 squared plus y squared plus 16 squared plus y squared equals 25 squared. We've only got one unknown, and that's y, and we can simplify this down. 9 squared plus 2y squared plus 16 squared equals 25 squared. Again, high school maths, simplify that down. All we do is minus 9 squared off each side and minus 16 squared, and that gives us 2y squared is 25 squared minus 9 squared minus 16 squared, which equals 625 minus 81 minus 256, which equals 288. Divide both sides by 2. Take the square root of both sides, and there's our solution there. Y is 12. We now know that From this bit of information, we can now simply again reapply this here and solve. We know that 12 squared plus 16 squared equals z squared. So z squared equals 400, so therefore z equals 20. Similarly, we know that 9 squared plus 12 squared equals x squared. So x squared equals 225. So therefore x equals 15. That's our solution. There's our unknown lengths. X, Y, and Z. X, Y, and Z. If you wanted to find these angles, again, you'd simply use your SOHCAHTOA rules. That's the entrance exam solved using high school trigonometry and basic mathematics, simply by having this instantaneous response of seeing triangles, a squared plus b squared equals c squared. Thank you very much for listening. I look forward to hearing your comments and talking to you again. Thank you.